Well, good afternoon, everybody, and thank you for joining us today. We will be recording today's webinar in order to share a link afterwards for anybody who would like to revisit the session or pass it along. And here at Carbon Solutions, we host a webinar on the fourth Wednesday of each month, and we share key updates in our monthly newsletter, so feel free to subscribe if you haven't already. Today's session will focus on the critical challenge of detecting and mitigating methane super-emitters with increasing regulatory pressure and tighter reporting timelines. Advanced tools like MethaneDART are more important than ever. I'm pleased to welcome my colleagues, BJ Brooks and Carl Talsma, who will be leading today's presentation. So with that, I'll go ahead and pass it over to them.
Well, hello, everyone, and welcome. My name's BJ Brooks. I'm a scientist here at Carbon Solutions. A little bit of housekeeping for anyone in the audience. If this is your first Carbon Solutions webinar, we'd like to welcome you again. And so a little bit of background about the company. We are a small business founded in 2021. We've grown to about 25 employees. Carbon Solutions specializes in consulting and front-end design and optimal siting of CO2 transport and storage infrastructure. We've added to our software and consulting portfolio over the years with tools like Nectar, which is specialized for direct air capture, and Locatia, which deals with industrial decarbonization and air quality, community air quality impacts. So welcome, everyone. But I'd like to talk today a little bit about methane detection and some of the recent advances that has happened in that area and what Carbon Solutions is doing. So I'll be hosting today for the first part and then handing over to my colleague, Carl Talsma. Next slide, please. So the framework for today's talk, I'm going to be introducing MethaneDART and covering some of the aspects of commercialization and getting into how MethaneDART is addressing some of that. And then I'll be passing it on to Carl. Carl will be going through some of the scientific framework for this project, as well as going over some of the preliminary results and even showing a demo of our web application. So next slide. So why MethaneDART? So we created MethaneDART to meet a growing need that we noticed for faster methane detection. Ways where the industry is really looking for ways to accelerate leak response as a way of keeping natural gas both out of the atmosphere and saving operators time and money. So this was a NOAA-sponsored project, a NOAA-funded project. It was funded through the NOAA Small Business and Innovation Research Program. We just wrapped up the phase 1 of that project, which was a six-month stint. At the end of January, we submitted our phase 2 application and are optimistically looking for a response to that. Next slide. So a little bit about the behind-the-scenes team involved with MethaneDART. We're quite cross-disciplinary. We have a core of folks that are working on AI and machine learning with also expertise in atmospheric transport modeling. So Carl and Yunhan Kelly. I myself, I've been working on a lot of satellite imagery and data procurement, as well as aspects of commercialization and business strategy for this product. Danny Rodriguez has been leading a lot of the atmospheric chemistry and satellite sensitivity to methane in the atmosphere, as well as market research. And we've been leaning on John Pren, who has been leading the UI, UX, and user experience, as well as software development. Next slide, please. So the two parts of commercialization that I'm going to start off with. The first part is going to sort of deal with the market framework, what's going on in natural gas markets and with methane detection in general, and some of the insights that we've gained through our market research. And then in the second part, we're going to shift to sort of what are the solutions out there for methane detection, and what this particular project hopes to achieve. So next slide. So, in general, methane market, the market for methane detection has a lot of market drivers, particularly in the area of satellite-based methane leak detection. So, as you can see in some of the images, natural gas infrastructure exists in a lot of different landscape settings. You can have this infrastructure in urban settings. It can be in mixed settings, both urban and natural landscapes, as well as remote places. And so what's really driving the demand for detection of natural gas leaks? So there's been an overall expansion of natural gas in the energy market. So natural gas has grown to comprise a growing share of our energy portfolio globally. And with that, there's been an expansion of infrastructure. And infrastructure, of course, in turn, has its own lifespan. And as that infrastructure ages, that can lead to leaks and therefore the need for regulation and ways of finding and mitigating those leaks so that it doesn't get out into the atmosphere. But there's also a second thing going on domestically here in the United States. So natural gas exports are also increasing at the same time. So the U.S. is exporting its natural gas abroad to global markets. For example, the EU has a different set of policies, in some ways more strict, and those in order to compete or to offer your product, if you're in the natural gas space, you will be subject to the regulatory and compliance pressures there. So there's a need for monitoring for MRV of methane in order to be accountable and to be efficient with your production. So next slide, please. In addition to that, though, we conducted interviews, market research interviews with operators and conservation groups and regulators, and we heard a number of things on their wish list that they consistently said that they wish they had. So, above all, what was needed was an improved, faster detection times, the capability to identify a methane leak event as fast as possible. So cutting down that response time to get to the point of concern and address that. Why that can be hard is a number of reasons. As you can see in these images, oftentimes natural gas infrastructure, in order to get it from the point where the source where it originates to markets where it can be consumed, it has to cover long distances, hundreds and thousands of kilometers sometimes. And so this infrastructure often occurs in remote locations. So there's a large area of land that is covered by some of this infrastructure, and it can be not only difficult to detect, but when you're using satellites take a certain amount of time to cover the entire Earth's surface. So the second thing that we learned from these market research interviews is the need. We heard that there's a strong need for high spatial resolution. So the ability to really pinpoint where a leak occurred exactly. That can be difficult because oftentimes in development fields, or in the case of transport, you have multiple operators that are operating within a field, within sort of a given area. And this is the natural environment. So you have wind shifts. And so wind can blow the leakage plume over somebody else's assets. So it can be quite complicated. And there is some difficulty in that. When it comes to pinpointing methane leaks and detection. Third thing is there's definitely a need for integrating methane detection solutions within the GIS workflows of the company. So this is as opposed to sort of solutions that are sort of rigid and sort of provide a rigid sort of framework or web portal. We're hearing that companies have their own ways of dealing with GIS data and with information, and they would appreciate one of the things that they think would accelerate things is the ability to drop a solution down within their own workflow. So something that was flexible that they could use in their existing systems. Fourth thing is nobody likes false alarms, so definitely need to cut down on the false positives. Nobody wants to make that call, get somebody up in the middle of the night, go and check something, and it turns out to be nothing at all. And then, of course, cost effectiveness is always a concern. Cost effectiveness can be an issue when it comes to satellite-based detection because commercial satellite imagery can be quite expensive. So, next slide. And of course, there's also the regulatory landscape of methane detection. So if you're in, natural gas is something that's used in a lot of industries. It's being produced. The operators in this area are under a lot of pressure for regulation. There are several different layers of that. There's national level, federal level regulation. There's also state level regulation, and then there's regulation in markets. And operators need to comply with all of these different regulations, and that gives rise to the need to be accountable to monitor that, to be able to pinpoint leaks and address them quickly. So multiple layers of regulation and compliance. There's another pressure, and that comes from the risk of loss of market access too. So if you're operating in a global context and you're exporting your product elsewhere, and you don't have access to the data, you don't have the ability to quantify or to assure that your product was produced with a low methane intensity. That means it was produced in an efficient manner where you didn't have a lot of methane leakage. Then you may lose access to those markets because some of these global markets are very particular about the efficiency with which the natural gas was produced. And then, of course, there's a number of different regulations federally and at the state level, such as EPA's new source performance standards that have to deal with newly installed infrastructure. And there's also the waste emissions charge, which has been paused, I guess you could say, somewhat, but is likely to be replaced by some future regulation. So there's a regulatory environment, there's a need for data, a need for being accountable. So next slide, please. So I'd like to shift a little bit and talk about some of the solutions that are available in this area so that you have sort of a context of what's available, and so that some of the results that you're about to see make a little bit more sense. Next slide. So there are a lot of tools and options out there when it comes to methane detection. Lots of different ways to do it. And so there are things that these solutions excel at, but there are still some gaps and some areas where we're hearing from operators that would be beneficial to kind of plug. So there's always a trade-off with any technology. There are no perfect solutions. There's generally in this area of methane detection trade-offs between speed and cost and spatial coverage. So just to take a few examples, that for when it comes to being able to detect methane in the natural environment, fixed sensors are one way that you can do that. You can install OGIs and fixed sensors on infrastructure, which gives you very, very precise readings on the amount of presence of methane and whether or not there's leaks in the area. However, deploying that across a widespread area, across compressor stations and thousands of miles of pipeline, that can be cost prohibitive. There's also aerial and drone surveys. So you can create a schedule and survey your infrastructure periodically and get high resolution aerial surveys. However, you're again running up against this issue of cost for flight time and operators and the episodic nature of these surveys. And then finally comes satellites. And so there's a number of different satellite methane detection service providers out there. I'm just giving one as an example here. So Carbon Mapper is one that's well known here in the United States. However, there's a 3 to 30 day latency in detection depending on which system of theirs that you're using. And it offers great insight. However, that can even as short as 3-day latency. This can present a problem when it comes to being responsive to a methane leak. That's several days, at least several days, in which the methane leak was occurring. And what MethaneDART wants to do is really cut down that gap. Next slide. So here's where MethaneDART comes in. We're really laser focused on accelerating detection of leaks in order to enable action by operators in the natural gas operators. So we're targeting a 1-day latency in detection. So we really think that this can support more timely action and getting to those leaks and mitigating them as soon as possible to keep that natural gas out of the atmosphere and keep it in the supply chain. We're targeting very high resolution capabilities in leak level precision in order to address accuracy and be able to assure that it's due to this infrastructure here and not the adjacent infrastructure. We're also building this in a smart way that is basically workflow ready. And so it will be by listening to feedback, partnering with those that use the software. We're trying to understand how this solution can drop down into their existing workflows as seamlessly as possible. And we're doing all of this in a phased rollout. So over the next couple of years through 2027, we'll be developing the software, refining it, working with early adopters to improve it prior to a commercial launch in 2027, and then looking at scaling beyond that in 2028 and onward. Next slide. So why now? Why methane detection now? So regulation of methane is on the rise. It's increasing every year. Every few years we have increasing regulation. And also, there's a lot of public visibility about natural gas leaks. There's increasing infrastructure out there. Public is very aware of this infrastructure. There are reputational risks associated with not addressing that. And so we also believe that the monitoring technology is ready and capable of addressing these issues. It's not perfect, but I think that it is definitely ready, and there are tools like artificial intelligence we can leverage to improve it and to get it to where it needs to be. And the last thing is all the stakeholders are aligned when it comes to methane leak detection. So the operators, the methane is a commodity to them. They do not want to leak. They don't want leaks to happen. Zero leaks is the goal because that's lost commodity. That's lost product. It also makes them less competitive on the global stage also. And conservationists and regulators also want to keep that natural gas in the product stream and out of the natural environment. And so we think MethaneDART is being built to meet this opportunity. And so with that, I'll hand it over to Carl, who's going to run you through the scientific framework of MethaneDART.
Thanks, BJ. I'm Carl Talsma. I'm a research scientist here at Carbon Solutions. And like BJ said, I'm going to talk about the tool MethaneDART and what we've been working on to kind of address this problem in methane detection. So the first slide here, this is a non-exhaustive list of satellite instruments that are capable of detecting methane or have been used to detect methane. There's more out there. There's like a dozen. And when we were looking at these, we wanted to narrow down the list to a couple of products that we could work with to kind of test out our workflow and see if it was feasible. One of the problems in this field is that there are so many instruments, and what we want to do with the tool is kind of aggregate all this data and have it all in one place. So the two instruments in the green there, Sentinel-2 and EMIT, are the ones we worked with initially. The ones in the orange are kind of ones we're looking at to work with next. And then the ones at the top are kind of not suitable for our problem exactly. We were looking specifically at point source emitters. So some of these products are have a broader spatial resolution and kind of look at more regional or global methane. Some of them are private and we don't have access to the data. And some of them have a low detection threshold. So the spectral absorption of the spectral bands of the instruments are not suitable to get a low enough detection threshold where we think it's worth pursuing. And you can see for EMIT and Sentinel-2, the spatial resolution is pretty low. We were looking for under 100 meters, basically, if we're trying to, pick out a single facility. We want really high spatial resolution. The return period for those two was relatively short, so about 3 to 5 days for either one. And that's something we heard a lot from oil and gas operators that we talked to, was they just want as quick a return period as possible, right? If you have a 15-day return period and you have a leak that could have been going for 12 days, that's not ideal. And then the spectral band, methane absorbs mostly in the shortwave infrared area. So emit is hyperspectral. It has really good spectral coverage. Sentinel-2 is multispectral and absorbs in kind of the right wavelengths. So that was suitable for us. And, the detection threshold in the literature is fairly low and low enough to where we thought it was worth it. So that's what I'm going to be showing. We did most of our workflow using emit initially. So that's most of the results are going to show emit. And then we started working on Sentinel-2 towards the end of the project, and we're kind of still working with that model. But this next slide shows the spectral signature of methane. So this black line across the top is the methane absorption coefficient where on different wavelengths of light. So you can see it's mostly absorbing in this short wave infrared over 2000 nanometer area. And then we also have the Sentinel-2 bands and the emit bands plotted. So emit basically has spectral coverage over this whole area in very narrow spectral bands. So we actually had to pick out which bands we wanted to use for emit. So we were using ones where methane was absorbing mostly. And then Sentinel-2, these blue blocks kind of represent where Sentinel-2 is detecting. And really only these 3 bands further to the right were suitable for methane detection. So that was mostly what we were working with here, was those 3 bands. And again, both of these products are fairly low spatial resolution, low enough to look at a facility and pick it out, and then pretty decent revisit time on the order of 3 to 5 days. Emit is on the ISS, so the orbital path is a little irregular, so that 3-day return period isn't always true. And then Sentinel-2, I think, is 5 days at the equator, and then as you move up in latitude, it gets closer to 2 or 3 days. So what we ended up doing with this, we know the spectral absorption of methane. We know how it interacts with light. We can use what's called the Beer-Lambert law, which relates basically the concentration of a gas within a column to the absorption of light that gas is going to absorb as light passes through it. And we can use that to take an image. We can model a methane plume using physical models and get the concentration coming from the plume. And then we can embed that plume in the imagery and know exactly how, given this concentration, this is how it's going to interact with the light that the satellite instruments are capturing. So what the setup of the problem is, we do all this physical modeling, we embed the plumes that we've created into this imagery, and then we take a machine learning model and we do some inverse modeling where we train the model on these embedded plume images, and we're able to back out the concentrations that we modeled originally or the emissions rate of the plume, and then apply those machine learning models to situations in the real world. So the first step of that is creating these physical plume models. We used a pretty simple Gaussian plume model. We wanted to create a lot of plumes that represented the possible ranges of different parameters, just basically the possible ranges of plumes that we would see in the real world. The downside of that is this is not, it's relatively simple modeling. It's not something like Hydran where there's more parameters and you're getting, graded wind speeds and things are interacting more. But we're able to produce a lot of plumes. So we kind of set a range of input parameters like wind speed, atmospheric stability, and we set a range where we thought it was possible. We ran those models, created 54 individual plumes, and then after the fact, we can adjust the wind direction, which is just kind of the orientation of the plume randomly, and then we can scale the concentration with the emissions rate, which happens afterwards too. And so we basically create this range of possible plumes. The emissions rate, we ranged from 100 kilograms per hour, which was kind of the base detection threshold that we thought we could achieve, and then up to 70,000 kilograms per hour, which is really high In the literature, I saw as high as like 35,000 kilograms per hour, but I just kind of went beyond that to make sure that the model could, latch on to patterns in the data. I don't know if that was totally necessary, but that's kind of what we were working with. So we had these 54 plume shapes basically, and then we kind of randomly changed the orientation and the emissions rate after that. Once we have those plumes, we start embedding them into the satellite imagery. So you can see this top left panel here is the results from our Gaussian plume model. And then we have the original satellite data. The way we went about procuring these images was we had a list of kind of reported methane plumes where we knew there was methane plumes. And we wanted to avoid those areas. We want an image totally blank of methane so that the machine learning model isn't picking up on things off in the corner. We wanted to train on exactly the data that we know. And then we limited the images by cloud cover. We limited them by latitude also. Where methane absorbs, water will also absorb. So having water vapor or clouds is not ideal. So it ended up being mostly in arid areas. But then using that kind of filtering, we collected 300 satellite images. And then using the Beer-Lambert law, we can embed those modeled plumes into the image. And then we put it in a random location and random orientation within the image. So you can just barely kind of make out where in the bottom left, you can see like a tiny little dark spot where the plume ended up being. And then we see the difference between the original image and the embedded plume image. And we ended up with about 2,000 training images for our machine learning model. And I think we could have, we probably should have created a lot more images. And we have the ability to do that. With the Sentinel-2 model, I think because there's fewer bands, we would have benefited from a larger data set. But that's kind of our plans for the future, working with that data. So for the machine learning models, we use mostly unit architectures. Units are used pretty often for image interpretation problems. And what a unit does is it has an encoder decoder path or a series of contracting convolution layers and a series of expanding layers. And the reason why it does that is it's picking up by contracting, it's picking up on features within the image. And then on the expanding path, it's reorienting those features to create a new image. So you can kind of, I could stare at this video for a long time. You can kind of see how it's picking out features within the numbers. They're being abstracted further and further. And then eventually you get the number predicted. So it's doing that on the contracting path. And then on the expanding path, it's kind of placing those features within the image. The reason we're doing that for our problem is hopefully the unit style of architecture will allow us to pick up on the shape of the plume. And hopefully that will improve our performance, knowing the shape of the plume and kind of what to expect from a plume image. It's unclear to me whether the models ended up doing that. It could just be using the spectral data. Like if we fed the model just pixel by pixel, all the spectral data, it's possible we could have achieved the same result. I'll show more on that in a little bit. Yeah, and then the basic setup is we have all of our EMIT satellite data or Sentinel-2. We have these 128 by 128 pixels images, and then we have 28 bands of data for EMIT that we're feeding into the neural network. We feed in 2,000 images. We did a training testing split, trained the neural network, and then we created several models. We created a model to predict the plume concentration. We created another model to predict just like the plume segmentation. So is this a plume? Is it not a plume? It's just ones and zeros. And then we had a model that predicted the location as well, trying to get like the center point of the plume. And then we also, not shown here, we had a model that predicted the emissions rate. So that's just, one value for each image or each plume. So that's the basic setup of how we worked through this problem, how we trained the models. This next section is going to be the model results. So how did the models perform? being trained on these plume images. First, I have the segmentation model. So just, is this a plume? Is this not a plume? The left panel is the original plume boundary from the Gaussian plume model. The second one is the plume predicted by the neural network. And then we have the error in this third panel. So you can see the model's doing pretty well. It's getting the shape, kind of that general shape, and it's, you know, picking out the plume pretty well. It's missing around the edges, but that's kind of to be expected as the plume spreads, the concentration goes down. You know, it's harder to detect the signal of the methane absorption through noise in the background. So this is doing great. This is just one image. This is what's called a receiver operating characteristic curve. So when we run these models, it gives us a probability of a plume between 0 and 1, right? And then we're able to set that threshold. Say we want, you know, very little false positive rate, we would set the threshold very high. And what this rock curve gives us is the ability to see what is the trade-offs between our true positive rate and our false positive rate. Generally, you score the area under the curve. So an area under the curve, this gray line would be 0.5, which means there's no predictive. The model's doing nothing, basically. It's not predicting anything. And a value of 1 is perfect. This left panel is our results for emit, and we have a score of 0.99, which is awesome. I think that's about as good as we could have expected to do. And then the panel on the right is Sentinel-2. It's doing a little bit worse, a score of 0.82. Again, I think what we were seeing is as we continued to train the model on images, we kept getting better scores. I think we just needed to expand our training data set a little bit. Obviously, emit has more spectral cover. I think we can expect it to do better, but I think Sentinel-2 would have benefited from a larger training data set. So we're still kind of working with that. And this next plot is the result of the concentration models. So this is just saying pixel by pixel how the neural network predicted concentrations on the y-axis are comparing to the Gaussian plume model concentrations. And again, this is with emit. This is doing really well. An R-squared value of 0.99, again, about as good as we can expect to achieve. You can see, like, towards the low end, the neural network is missing some of the concentrations on the low end. And again, I think that's kind of to be expected. We expect the model to do worse as the concentrations get really small and we get closer to that detection threshold. But the model's also kind of underpredicting on the high end, which I think is because there's some saturation happening where you get, you know, enough methane where most of the light is being absorbed, and you're not really differentiating much on that high end between, you know, a lot of methane and a lot of methane plus a little more methane. So we're getting some pixel saturation, I would say, on the high end, but overall doing really, really well with the concentration model. Here's the results of the concentration model for a single image. Again, it looks really good comparing these two images, and you can see the error on the right, kind of missing at the center of the plume a little bit, but overall doing really, really well. And then here's all the models together. The location model did not perform as well. As you can see, there's more error. And the way I trained this was using a decay function where the values kind of decay, moving away from the center of the plume. And you can see that the model is kind of using the concentration because it's non-symmetrical. The plume is non-symmetrical and it's kind of predicting more in the direction of the plume and not away from the plume. This is where I suspect that the spectral data is maybe more important than the shape of the plume, and we're not getting that much added benefit from using our UNet architecture. We could figure this out pretty easily by just feeding a model 1 pixel at a time, right? We just didn't get to that, but overall the models are all performing really well. And for our workflow, we didn't end up using the location model much because, using the concentration model, we can kind of see generally where the center of that plume is anyway. And lastly, we have our emissions rate model, which is kind of I don't know, a really important piece to me was seeing how this emissions rate model, this is like a much harder problem to solve than just concentration rate, because it's kind of taking the whole image into account and trying to distill all that information into a single emissions rate. And it does really well. Our R squared here was around 0.8, I think. So there's a little more spread in the data, but overall, I think it's predicting it pretty well. There's definitely some value in what the model is doing here. Yeah, so that was basically the breadth of our modeling work using the machine learning models. And the next step, right, this is all using synthetic data. The next step was kind of to see how the models perform in the real world. So we started running the models on imagery where we knew that methane plumes existed from the literature, from kind of reported sources, from other people's work in this field. So this is the first image we ever ran it on. And you can kind of see there's this oil and gas infrastructure. We ran the model over this area, and you can immediately see where the methane is popping out and how it matches up with where the infrastructure is, which was really exciting to see. Really cool. This is actually in Syria. It's kind of far flung. The next thing we did was run it for all of the known plumes in the United States, or a big set of them. And what we realized running this is you end up getting really complicated scenarios where you've got two plumes really close together. Sometimes they're overlapping. Sometimes you get a different time step where they're not overlapping, and kind of choosing what our definition of what a plume is, and how that plume evolves over time, and kind of separating those was a pretty hard problem to solve. This next slide, this is just a imagery from the Permian Basin in Texas, and you can see all the oil and gas infrastructure, and it's all just like jammed in there. So you can imagine if there's a plume from one of these well pads and a plume from another one, it's pretty easy for them to overlap. But essentially, yeah, the question, what are the known plumes? Yeah, some of them are from other monitoring efforts like Carbon Mapper. There's other data sets, like there's the GHGRP, where people report their methane emissions to the EPA and stuff like that. We have our own data set called Concord, which aggregates not Carbon Mapper, but some of those other data sets where it's reported emissions. So there's reported methane emissions. We use that. We use stuff from Carbon Mapper. It was a variety of data sets, but yeah, that's right. So we ran it on this set of data. It wasn't a comprehensive set of data, but we were able to find 1,260 plumes kind of immediately. And then we had to build in these heuristics for, okay, the segmentation model gives us a probability. What probability do we want to set to say this is a plume? What do we want to do when these plumes overlap? How do we separate them in time and space? So there was a lot of hard work happening towards the end of the project that we're still figuring out a little bit. And then kind of something we're working on now is just using real world data to validate our models that we trained on synthetic data. So there's controlled release experiments is really the best way to do this, where someone is releasing methane at a constant rate and times it with a satellite overpass. So you get an image that you can validate with on the ground data. There's not a ton of those experiments, and they have to line up with the instruments that we're using, right? So that kind of match is hard to do. We're working on that right now. But for now, we can run our models on anywhere in the world when those satellites are going over, and trying to work on getting some better validation data. And then this last slide is kind of just a schema for how our software is set up to work. So we pull in data from these satellites, run it through our neural network models, and then we take some of this ancillary data from the NEI. Concord is our software. Their Carbon Mapper is a similar effort, and then we can attach other ancillary data to the plumes that we're finding, like what kind of facility is this? Sometimes who's the operator of the facility? And then we put that into a database that we can access through a web hosted user interface. We built a prototype user interface that I'm going to show. I'll try and share that. And the goal is to have the goal is to have, the satellite data be processed as it's coming in. So, if Sentinel-2 picks up an image today, it gets automatically processed by our models, and we have the results of that. Right now, we have just been running on those known plume locations. So, the goal is to have it running autonomously. But for now, we can pick anywhere in the country, run the model, figure out what our results are. So that's where we're at right now. We're trying to automate the process. Okay, I'm going to share the GUI, what it looks like now. So this is a prototype. It's still a little rough around the edges, but it's just kind of a proof of concept, like to get kind of this workflow started. So we can kind of zoom in on some of these plumes. If we zoom into the Permian, we can click on one of these, and the plume concentration should pop up, so we can see the plume. The emissions rate is here. These values are obviously not correct. We're still kind of working on getting the emissions rate model incorporated here. But you can click around on these plumes. This website is open. Anyone can access it. I wouldn't, do anything with this data. It's not, like I was saying, we haven't validated using on-the-ground data yet, but you can see kind of how it's generally supposed to work. You click on the plumes, you can see the plume data, the plume concentration pops up, you can see these different plumes. And we're definitely seeing that. So this one is an example of, it's hard. This kind of looks like two separate plumes, maybe. It's hard to say. This is kind of where those heuristics come in. And you can say we get a couple of time steps here where it's picking up the same plume. Yeah, so this is our prototype for now. And then we can filter based on different kind of facility types. This was our prototype. It's still a little rough, but we're working to make it better. And for now, really, we're focused on trying to validate the models using real world data. And then, yeah, we can, zoom in on a specific facility and kind of tell a client, what is the emissions rate? How is this evolving over time? We can get the data just for that point and let them know how their emissions are changing through time, basically. Let's see. Yeah, so that's all I have. Yeah, we're happy to take any questions. And let's see. I'll pull up the presentation again. I've got our contact data there. And yeah, happy to answer questions. And then happy if someone wants to email us and ask questions that way. Happy to do that as well. I'm having trouble bringing the presentation up, but
yeah. Looks like we got a couple questions in the Q&A and also in the chat, and I partially responded to them, briefly responded to them there. So one of them was, has the U.S. terminated recent EPA regulations that were charging fees for oil and gas leaks? Is the industry challenging this? So this goes back to this question about regulation. And so there was the primary regulation that natural gas operators were concerned about was the EPA's waste emissions charge, which started out at, I think, $900 per metric ton of emitted methane and ramped up over time. It was supposed to start in 2024, but wasn't actually going to be implemented until like the end of the year. It was kind of in flux, and it was part of the Biden administration's bill. So that got so that both House and Congress passed to repeal that. The president, I did look it up. The president actually a couple of weeks ago signed it, so that has been effectively nullified. But the original language for the waste emissions charge is still in that bill, and so they haven't completely removed it. It's just not going to be enforced by EPA. So we're kind of in this pause state, is what I was referring to in the presentation. So hope that answers that question. And then we had a second question in the chat about known plumes, and I just wanted to quickly say I think we forgot to mention our partners at St. Francis Xavier University, the Flux Lab, and we've been working with them actually, and they do a lot of work on methane leaks in the field, especially with landfills. And so we've actually worked through, we have a large list of known and well quantified methane leaks. And there's even a facility that we toured at Colorado State runs it. It's called METEC, where they actually do controlled releases of methane in the environment. So,
yeah, so we got another question. I understand that a major challenge and uncertainty in satellite monitoring is good wind data. How are we addressing that challenge? We didn't use wind data for this round of modeling. One of the reasons was we were focused on that low latency time. That was one thing we heard in our market research interviews is we want low latency time. If you're trying to find like a high spatial resolution gridded wind product, those take time, like using reanalysis data, that takes time to build. I think in the future, so using that data would lower our latency time. We want results as fast as we can. I think in the future, obviously wind is important. In the future, I think we're going to try and use forecast data that is like available immediately, right? And I think, I don't know, I'm optimistic that just any wind data, even if it's not entirely accurate, using the forecast data will improve the models. Just getting the general wind direction is going to be important, is going to help. Getting the general wind speed is going to help. But for now, we were not using any wind data. And I don't know, it's something we're going to work on in our next round of kind of modeling overhaul. And then another question, can you share more about control testing? Are you participating in Stanford's or other efforts? Yeah, so Stanford did a series of controlled release experiments, and they kind of asked several teams to do some blind testing using their model results. That was a while ago. We're not like to that point quite yet. But as BJ mentioned, METEC, they have historically mostly done like ground-based observational testing and smaller control release. They're planning a series of larger satellite scaled control release experiments, and we talked to them a little bit about that. Yeah, something we're working on. Another question, so would the one-day product just be a detection product, or can you develop emissions rate estimates absent wind? Okay, yeah, really good question. So the thing we heard from oil and gas operators is, particularly midstream like pipeline operators, was that they don't care so much about the emissions rate. They just want to know if there's a leak or not, to a certain extent, right? So we are planning on having like, the best detection product, the fastest detection product we can. And yeah, maybe taking a little more time to develop that emissions rate modeling. Maybe we do use some of the better wind products for that. But just for detection, there seemed to be a higher value on getting the results really quickly. Whereas for the emissions rate model, like Carbon Mapper, they were contracting with the government as part of this waste emissions rate charge to really get high accuracy quantification of the emissions, right? So they're going to take as much time as they need to, and then those charges come down, as they're getting the data. So they don't really have an incentive to lower their latency as much. Whereas if you're working with the oil and gas operator side, they're trying to find these things as fast as possible and fix them. So I think that's the differentiation between those products and the product we're trying to build is we want something that's working as fast as possible, that can result in, that has actionable results, right? Where we're detecting the plume, we can fix the plume as fast as we can. Yeah, thanks.
Yeah, and that particular question, I feel like there's so many trade-offs when it comes to detection time. It's kind of like, you're a puppeteer and there's so many strings to pull on. There isn't an optimal way, but in the interest of time, I think we do have a couple of more from the Q&A, and one is, you may have mentioned this, how are you classifying facility types? What data is used for that facility identification?
Sorry, can you, I didn't hear you. I was
Okay.
trying to put down BJ.
The question is, I think the question is relating to pulling in some of the ancillary data sets like Concord and stuff, and how are we calculating, or how are we classifying facility? How are we pulling in
Oh,
that data
yeah.
to classify?
Yeah, so yeah, we're pulling in that ancillary data. Basically, we're just location matching. Does this location match up nicely with stuff we're seeing in these other data sets? And then we can use the facility type from those data sets. It's not perfect, but that's what we're working with right now. We had talked about previously doing some more machine learning where, training a model to recognize different facilities, like, is this a well pad? Would be like something you could do with a machine learning model. We're choosing the easier route for now for that one. Are you modeling absolute CH4 concentrations or values above background? We were just doing absolute for now. And then I think we had one more question in the chat. Can you highlight which methane sensor is widely used for measurement with high accuracy? Yeah, so I don't know. I can refer to that table that we had. Really, EMIT gets used quite a bit because it has a lower detection threshold. I think there's a bunch of different products and there's different reasons to use them. We were at the end of the project, we looked into Worldview 3, which is a private product. It's expensive to buy, but that is very high spatial resolution. It's multispectral in the right areas and is, a 1 to 3 day return period. It's really expensive though. So, I mean, you could get really accurate estimates using that data, but you have to pay for it. So for now, we're working with EMIT and Sentinel-2. There's other projects. Tanager was just launched, and there's data coming in. That's also a private product that you have to pay for. Yeah.
Yeah. And just to add to that, so there's many different satellite methane detection service providers, and they all use different combinations of private and public satellites. But basically, you want to use bands that are very sensitive to methane in the atmosphere, and use adjacent bands as adjacent as possible that are insensitive to methane in some combination. With machine learning, you can kind of get around that a little bit and let the algorithm kind of figure it out. But you have to remember that a lot of these satellites are purposed for different sort of looking at methane in the atmosphere for different reasons. Like EMIT, for example, was originally it's for land surveying, geological surveying, whereas Sentinel-2 is very multi-purpose. So the width of the bands is very different, as opposed to something like, GOSAT or GHGSat or something that's sort of, geostationary or something like that. And so there are trade-offs in all of these, but generally the commercial satellites offer high spatial resolution and pretty narrow bands. And it's up to you to kind of choose the bands that you choose to use. But then probably even more importantly than that is revisit time. So how can you get the images that you need covering the assets that you want to cover? It gets very, very complicated when you're talking, about tasking satellites to look at specific places. It's kind of a huge mess, and so the idea is to take that out of the hands of the operators, because it's a full-time job, and sort of develop a system that does that in an optimal, cost-effective way. So yeah.
Have you tested this in more urban areas? The two examples you showed were pretty rural, with most of the structures being related to production. Yeah, we were focused mostly on production. We haven't, tested stuff like I was saying. We haven't tested stuff in the real world too thoroughly yet. So working on that. One thing for an urban setting, one problem that we would expect to have is kind of building footprints and how the plume would interact with buildings. Like if you're really in a dense environment, that may be something to think about. But yeah, we haven't gotten to that step quite yet.
Yeah, and sort of urban settings that's generally covered by sort of downstream natural gas. So those are the final delivery of natural gas, and they're kind of in a little bit of different regulatory pressure. Those leaks tend to be smaller, spread amongst businesses and houses. It's kind of a different, more accessible. Like you may leverage some more stationary monitoring solutions, cameras and those kinds of things for those sort of situations. Yeah.
Yeah, we have our other software tool, Locatia, which is really concerned with urban air pollution. They're doing a lot of plume modeling using high split in urban settings, looking at like PM 2.5 and SOx and NOx and stuff like that. So we're trying to kind of integrate those two tools a little more and incorporate some of the machine learning work we've done here with that project. So it might be something we are more interested in moving forward.
Okay, I'm gonna jump in here at the end all and wrap it up. Carl, would you mind going back to the slide with your all's contact information on it?
Yeah, no problem.
If anybody has any follow-up questions for Carl and BJ, please don't hesitate to reach out to them via email. Another reminder, we host these on the fourth Wednesday of each month, so don't hesitate to follow our LinkedIn and newsletter to keep up on what we have coming out. Thank you all for joining us. You'll receive an email follow-up with a recording as well as a link to our YouTube that will house this video. Have a good rest of your week.
Thank you, everybody.